The next indeterminate form we're going to look at is the one 0 times infinity. Now in the guidelines provided in the notes, it gives some indication of what to do, and we'll work that out in the example here. Example number 6. The limit as x approaches 0 from the right of x squared times the natural log of x. Alright, if we try to plug in 0 into x squared, that's obviously going to be 0. But if we plug 0 into the natural log function, or look at the limit as it approaches 0 from the right, we see that that's going to be negative infinity. So I'm just going to write 0 times infinity. And if I wanted to be technical, I can put the negative out in front, remembering that this is just notation to let the reader know that you recognize the indeterminate form. So I like to write 0 times infinity. Okay. If I haven't confused you enough, let's continue the example. So what does L'Hopital say about this form? X approaches c, let's call this f of x times g of x, and that led to the 0 times infinity. L'Hopital said, well, we can just do some clever manipulation. What about making this f of x over 1 over g of x? See, that's nothing new to us. That's simply maintaining the quality of this expression. See, if I multiply the reciprocal, I get this back. So this is just a clever manipulation. So then instead of having 0 times infinity, this would give us either 0 over 0, or it would give us the infinity over infinity. So that's what we need to do here. So this is going to equal the limit as x approaches 0 from the right. So I need to keep one of these two, let's call one f and one g. We need to keep one of them at top and write the other as a 1 over reciprocal in the denominator. And because of the nature of the derivatives, I will highly suggest that you keep the natural log on the top, and then the bottom here would be 1 over x squared. So now we have the indeterminate form that this is going to negative infinity, and now 1 over x squared as x approaches 0 from the right, that function is going to do this, and so that's going to approach positive infinity, which is, like I said before, I like to write the negative outside, and then infinity over infinity. I like to write it like that. Anyhow, let's do L'Hopital's rule. So L'Hopital says that now that we have the good old standard indeterminate form, infinity over infinity, I'm going to take the derivative of the top. So the derivative of the top is 1 over x. And I'm going to take the derivative of the bottom, which is going to be negative 2 over x to the power of 3. So now, if you remember me saying, if you can simplify, then you must simplify, and so we shall. The limit as x approaches 0 from the right, I'm going to rewrite this as 1 over x times x cubed over negative 2. That's not L'Hopital, that's good old-fashioned. Alright, I will simplify this to be x squared over negative 2. And when I plug in 0 now, because I am permitted to, I see that this limit is going to 0. Example 7. Okay, we see that we have the indeterminate form. The first parenthesis expression is going to be 0, and then the secant of x, as we showed in an earlier example, is going to go to infinity. Nice and clean. 0 times infinity. So let's be clever. I'm actually not doing L'Hopital here. I'm just doing a clever manipulation, keeping one on the top and bringing the other at the bottom as a reciprocal. So I hope you see that leaving this on the top makes sense. And then on the bottom it would be 1 over secant, or simply cosine of x. So now when I do some plugging in, I've got 0 over 0, standard L'Hopital's rule, limit as x approaches pi over 2 from the left, the derivative is going to give me 2. The derivative of the bottom is negative sine x. When I plug this in, it's going to give me 2 over negative 1 for a limit of negative 2.